So hey everyone, I am back with another video, and today I got an interesting topic with me, something that I have been pondering upon for a while, and that is how did humans arrive to calculus? Like how we derived this thing, how we figured out how to find the rate of change of something mathematically, because mathematics seems discrete in numbers. How can we use something discrete to find that is something continuous? And to find that answer, I went all the back in history to our good old friend Isaac Newton, and I was mind blown by the strategies that Isaac Newton used to derive calculus. So, as you know, Isaac Newton was an obsessive scientist. Like, he studied everything to its little detail and studied obsessively for years and months and years upon end. So, Newton was trying to understand motion, and motion is fundamentally continuous. You can't see someone here and then just snap over here. It's a continuous way from point A to point B. They don't just snap, they move continuously. So, to figure out motion, Newton needed a framework to use mathematics to figure out a continuous quantity like motion. So, what he did is a bit tricky to wrap your head around, but it is genius once you understand it. So, let's imagine uh, the motion of an object. Let's see a curve on a graph, which is common for most types of motion, and let's pick a point on that graph as a ball. So here's this curve on a graph, and there is a ball, a point from the start. Let's see how this how the rate of change of this ball occurs. So let's say this ball was here and it moves it an infinitely small amount to the right. So it was here and it displaces that by an infinitely small amount, or vanishingly small amount, as Isaac Newton called it over here. So the first y was equal to x, now y is equal to x plus o. Y was equal to x square, now y is equal to x plus o square. And as you know that when we have an identity like x plus o whole square, then we can apply the algebraic identity. So we would come with a sum that gives us the rate of change as 2x. So from here to here, the change in x, the change in y, the change in the y quantity was 2x. So now, since O was such an impossibly small quantity, the displacement was such an impossible quantity that we can even ignore it and just focus on 2x. Now, I know it might be a little bit hard to wrap your head around here, and you definitely, I would highly encourage you to go on and do your own research, ask AI about it, or read articles on your own, because it is a really interesting concept about how we can use infinitesimals and very small quantities and then ignore them to find the rate of change, and how we figure out the rules of differentiation. Now, for integration is also same thing. Let's imagine a graph like this, and to integrate we have to find the area under the graph. Now let's take another ball for example, and let's say it moves again by infinitely small o. Now imagine this, the ball moved from here to here an infinitely small amount, so this width of the area that goes down to the x-axis will also have an infinitely small width, because the displacement of the ball was so small. So the area, the width of the rectangle that forms when we go down to the x-axis will also be infinitely small. So we can calculate the areas of each and every position after every infinitely small step like this. And once we have calculated, we can ignore the infinitely small amount that comes as the final calculation, and then we can keep the final result as the answer. So that was very fascinating, extremely fascinating for me. How can a human brain just come up with this? So I hope uh, that you like this video and you learned something new, or at least I inspired you to learn something new about these topics. See you in the next video. See you later.